Hello, I'm Vasco, and I'm going to be presenting the context-aware efficient message propagation by Pedro Alves and Paulo Ferreira. So, watching a radical change in the type of packets that travel on the internet, namely Facebook and Twitter, have brought a massification of personal short messages, also known as posts. These messages are actually contextual messages. They have information about the identity, time, and location of the person sending the message. Since these systems usually have hundreds of thousands, if not millions of users, we are talking about a huge volume of information being sent to the server. Um, a server must be able to propagate this context to whoever may be interested. So we're gonna try and look on how we can take advantage of these contexts to more efficiently propagate messages. Let's look at the following problem example. Let's imagine we have a friends nearby application that tells the user which friends of his are in the same location as him. This seems simple enough, but every time the user changes location or their friends changes location, this matching rule has to be updated in the system. And if a large number of users are using this application, the system or the server will be bombarded with messages, which is not really that great. Let's look at how current approaches would deal with our example application. With a publish subscribe approach, every time the user moves, the client application would have to send three messages. Assuming the application is being used by a lot of users and the user is constantly moving and changing location, this will lead to wasted resources and poor scalability. The multicast approach has the same problems as you can see in this slide. As a solution to this problem, this paper presents Radiator, a context propagation middleware that combines the concepts of delayed propagation and aggregation to improve the performance and scalability of context-aware applications. The context propagation is controlled by functions that, given the context of the recipient, dictate in which conditions should a given message be propagated. We're going to step in on what delayed propagation and aggregation means in the next slides. Let us imagine an application that shows the most popular spots nearby the user's current location. Popular spot being a place where, let's say, at least 10 users are in that location. So in these messages, the context will be the location. So what we can do is, instead of sending the location of each and every one user, which is unnecessary because we don't care about users that are alone in a specific spot. We want to know only about the users that are in a popular location. We want to know about aggregated users. So the system will aggregate all the messages in the same location, and like we said before, considering that a popular spot is a spot with at least 10 users, the system will wait to watch 10 users in the same context, which in this case is the location, and then propagate that one message with all the users. So having this, instead of propagating n messages, each one saying this user is now at this location, we only need to propagate one message saying all these users are in this location. This is what context aggregation means. We aggregate all the messages under the same context and aggregate them into one message to then be sent. Delayed propagation meaning we don't automatically and instantly send these messages. So we wait until we have a considerable number of messages under the same context to then propagate only one message. These aggregability functions used by Radiator receive a value. This value can be either volume, time, or people. This defines the minimum number of messages under the same context that has to be aggregated before the propagation begins. Using the time value, we can choose to aggregate all the message within a time frame and then send it after the time frame has completed. As we can see in the first row of this table. We can also add some conditions to these aggregability functions. If we look at the third row in this table, um, let's imagine the nearby friends application that we talked about earlier. Let's assume the user wants to know immediately where their friends are, instead of waiting to have 10 messages aggregated. We can set the number of aggregated messages for random people to be 10 before being propagated, but if one of the users is a friend, it will be automatically or instantly propagated. Let's look at the Radiator architecture. Every client will have a middleware that acts as a pluggable component to applications that completely abstracts away the application from the underlying propagation infrastructure. Radiator will also have a server, which has three main responsibilities. First one is clients management, which keeps track of all clients of the application, namely their ID and IP address. Most importantly, it manages the current context of every client, which is crucial to the context aggregation process. The second responsibility is context aggregation, which applies the aggregability function to every incoming context message, providing both the sender and recipient's context. It also manages the list of retained messages and the thresholds at which messages are no longer retained and start being propagated. The last and third responsibility is context propagation, which delivers the context messages to all clients triggered by the context aggregation component. The delivery can be done using direct connections to the clients, peer-to-peer propagation between clients, or a combination of both. We are looking at a centralized approach where the server is responsible for pushing messages to every client. While this is quite simple, if the number of recipients is large, the server starts suffering from scalability problems, since it has to push the message to everyone. To deal with this problem, Radiator introduces an alternative propagation mechanism that is highly dynamic. All clients that communicate directly with other clients send an attribute, peer-to-peer enabled, to the server when they register themselves into the system. When a message is propagated, the clients that do not have this peer-to-peer enable attribute will simply receive the message as seen before. However, the others will be divided into groups of k elements. Each group is processed as a chain of peers through which the message must get through. The message is propagated from the server to the first peer, which then propagates to the second peer, and so on and forth. As you can see in the slides, instead of the server having to send 5 messages, it only has to send 3 messages, since client B will propagate the message to client C and client D will propagate the message to client F. To test Radiator, a traffic monitoring and hazard detection application was created. This is a good test case because there are a lot of cars per day on the US expressways, for example. Cars in transit are most of the time changing their location and speed, which means changing their context, which is good to experiment how well Radiator deals with these frequent context changes. In this slide, we can clearly see how the aggregability function value affects the outbound bandwidth. We can clearly see that the more messages are retained before being sent, the lower the outbound bandwidth is. Not only does the average outbound bandwidth decrease with the increase of aggregated messages, but also the average lag decreases, which is pretty good. Here we can see how the alternative propagation mechanism used by Radiator of having peer-to-peer clients propagate messages by chains can influence the outbound bandwidth. Looking at the graph to the right side of the slides, we can see that having bigger chains greatly reduces the outbound bandwidth. Bigger chains meaning bigger groups of peer-to-peer enabled clients chaining or propagating messages between them. While this greatly reduces the outbound bandwidth, unfortunately it increases the average lag because the clients at the end of these chains will receive the messages uh, with some delay. This delay being increased obviously by the size of the chain. So from the previous slide, we concluded that the chain size of 1% was the one that reached the best compromise between bandwidth and lag. We will now experience this peer-to-peer mechanism with the aggregability functions. Uh, in the second column, we have the settings, which show the minimum number of context messages that have to be aggregated before the message has to be propagated. We can see that aggregating messages has the same effect it had in the non-chained experiment. The lag decreases from vol 1 to vol 20, and while it increases again with vol 50, it remains smaller than the vol 1 lag. Since the server is sending much fewer messages, and note that these messages are bigger as they now carry the chain of recipients, the server's network link is less stressed, allowing a greater throughput. Unlike current selective message distribution approaches which rely on relatively stable sets of matching rules, the Radiator approach relies on functions that, given the current context of sender and receiver, decide under which conditions a message should be distributed. By combining both aggregation and chain-based propagation, Radiator was able to reduce the server's outbound bandwidth by 20 times without penalizing the average propagation delay in a given scenario. This is the end of my presentation about Radiator. Hope you enjoyed.